So I appreciate you all coming along this evening. My name's John, and Naomi twisted my arm, so I happily came along. Just to give you a little bit of background for myself, I used to be a professor. Well, I first of all was a mathematician, then became a professor in computer science. I got my PhD in computer science. And then actually taught not far from here at the Oregon Graduate Institute, OGI. And then I started a company called Galois, that's how you pronounce it. It's named after the mathematician, Évariste Galois, whose life is amazing. If you're not aware of his life story, you should read it. It's amazing how much he accomplished before he died in a duel at age 21. So, I mean, it's a tragic story, and yet he's actually revolutionized all of modern algebra comes really from his work. All of cryptography comes from his work. I mean, it's humongous what we do. So anyway, I was working at Galois, and we've been there 20 years, just downtown Portland. And then I took 3 years out to work for the Obama administration in the organization called DARPA, which is the Defense Advanced Research Projects Agency. DARPA is fascinating, particularly from an electronics and software point of view, in that almost everything that comes into this actually had its origin in DARPA programs. So VLSI chips, DARPA funded that whole way of putting transistors together and making chips. Even through to Siri on this, that was a DARPA program in 2005 that was being run by SRI. And then they spun out a company that they called Siri, and then Apple bought it and so on. So it's a way that you can have tremendous influence. So I was just telling the guys, I spent about $550 million every year of your money, thank you very much, in cybersecurity and artificial intelligence. And so one of the things that we needed to do, talking about artificial intelligence, is make sense of the landscape of artificial intelligence, and that's where this talk came from. So this talk, the early version of this talk, it was first presented to about 500 or 300 employees at DARPA, and so this is sort of you're getting the good stuff today. So what I added also a little bit is every now and again through this talk tie into some aspects about the AI and the mathematics, the link to mathematics, so that you can see, that's why I might study this part of mathematics, or that's why I might study that part of mathematics. So that's the plan, and I think we'll go till about 7:30. Is that right? And I'm very happy for you to ask all sorts of questions, for you to object, for you to say, hey, I didn't understand that. Can you repeat it again? I like that kind of interactive flow. We good? So let's get going. Yeah. Oh.
Give me thumbs up.
Perfect. So AI, artificial intelligence. I mean, you hear all sorts of crap about artificial intelligence, right? And part of what I want to do today is demystify it and just say, at its core, what is it that's going on with AI? So if it's artificial intelligence, it's worth us thinking a little bit about intelligence, because if we're going to have artificial intelligence, what is actually intelligence? And so one way that you can think about intelligence is it's actually an ability of a system, whether it's a biological system like you and I, or whether it's a computer system or any other kind of system, it's the ability of that system to process information, to take in information that might be really subtle and nuanced, and do something interesting with it to output stuff. And then as you start thinking about it more and more, you realize that there's more than just one dimension of that ability to process information in nuanced ways. In the early days in computer science, they had this notion that if we ever built a computer that was smart enough to play chess, then wow, that would just be the most intelligent thing on the planet. And then we realized, no, you can do algorithms to make computers play chess, and they're still pretty, the old chess computers and so on, they're dumb. I mean, they can play chess, they can kick your ass at chess, but they're still dumb. So here's a way that we might think about different dimensions. One is when you take in data, whether it's visual data or audio data or statistical data or anything like that, what can you perceive out of that data? What sense can you make in terms of what that data is telling you, what the structures? Like when I look at something over here, immediately my brain is identifying that there's a vertical line there and a vertical line there, a horizontal there and a horizontal there. It's doing a lot of that processing to make sense of that basic signal that's coming. So perceiving on the input data is important. Another dimension is learning, where you're able to take stuff that you've applied, that you've gained in one situation, and apply it to another situation. Another dimension, actually I'll do them in the other order. Reasoning. Reasoning is like, Sudoku and those kinds of things, where if this, then that, and I can follow the implications through and see where it's going. And that's what we tend to think of as intelligence often when we say somebody's intelligent. You may say that they've got good reasoning abilities, but it's just one of the dimensions. And then another, I'm calling it abstracting. Abstracting, that's actually at the core of what mathematics is. Like, let me give you an example. 3. What is 3? I mean, it's really quite fascinating to try and think, like, does 3 even exist? Like, what does it mean to exist? So if I'm thinking about the notion 3, I start to realize that that's an abstraction of how many people are in this row. For example, that's one way of expressing 3. And then I might find, if there were 3 chairs over there, that's another way of expressing 3. And then I start to maybe formalize what I mean by the notion of 3. But abstraction sort of says there's something fundamental about, even though there were people over here and chairs over there, there's something that's the same there. And abstracting is being able to take the essence of what's the same out of the noisiness of everything that's different. It's sort of detecting, it's a little bit like perceiving taken up to the next level. So these are the key ideas of intelligence. And one could add a few others. Now through the talk, I'm going to imagine a scale, just a 4-point scale. Sort of think of human ability as being out here on the right-hand side. And then we're looking, as we're doing different parts of artificial intelligence, how good can we make the machines in their perceiving? How good can we make them in their abstracting? How good can we make them in their reasoning, and so on, so that we get the sense of it. So intelligence is the ability to process information, and artificial intelligence is just when you program that ability, particularly dealing with real-world information. Now, I'll just say an aside, for those of you who are sci-fi fans, sci-fi has this idea, like Commander Data, if any of you ever watched the old Star Trek Next Generation, like became intelligent and then became sentient, became aware, and so on. I think there is no connection between increasing intelligence and sentience. We have examples of that, like a newborn baby is not particularly intelligent, but they are sentient, way more sentient than this iPhone that has huge abilities in terms of intelligence. So it's very valuable to think of sentience that is being aware, having experiential, felt experience as different from intelligence. So that's just an aside. Don't think of intelligence as being the same as the nature of being a being, if you run out of words in this way. Okay, so I'm going to argue that there are really 3 waves of AI, and the first wave used to be traditional AI, the second wave is the one that's hot at the moment, and the third wave, we're just starting to see glimpses of what it might need to look like, and a lot of it needs to be invented. So we're going to walk through each of these, and that's the structure of the talk, is these 3 waves of AI. So the first wave of AI is where you set rules to describe knowledge. I like to think of it as you handcraft knowledge. So I talked already about a chess computer. In a chess computer, what the programmers will do is they will say, here's where the board are, this is what the moves are, here's a strategy to do this. Here's another thing where you might not be sure what to do. Why don't you follow it ahead a number of steps and see what it's like, and now follow that ahead a number of steps. And so all the time you're writing a program which is reflecting the knowledge that, in some sense, that the programmers have. They're trying to craft the nature of knowledge. I love TurboTax as an example, coming into tax season. Maybe none of you do your taxes yet. It's a joy of adult life that you get to do your taxes, and or maybe you don't get to do your taxes ever. But TurboTax, you've got this hugely complex tax law, and what the makers of TurboTax have done, they've distilled it to a set of rules where you put your inputs in, and these set of rules go through and they trigger and they fire, and they essentially take that handcrafted knowledge of the tax law, and they're able then to construct your return for you. So that's the nature. If we were to look at a set of rules, you might have rules. This is taken from a very simple, what's called an expert system. Again, old style AI. If the thing that we're looking at, query X, has wings, then it's a plane. If it flies, then it's a plane. And you might say, yeah, I disagree with these rules, but that's not the point. You know, imagine some sort of set of rules like this. If it runs on tracks, then it's a train or a tram. R4 is interesting because it might build on a fact that it established by another rule. Like you've established that it's a plane, and now rule 4 says if it's a plane and it can take off vertically, then it's a helicopter. And so you can see you're starting to have lots and lots of these rules. And expert systems turned out to be quite good in helping doctors diagnose various diseases. That experts in those diseases would say, if you've got this symptom, then probably this thing is happening. And you know, you get hundreds, maybe even thousands of these rules. And then what the doctors would do is they would input the symptoms, and the expert system would say, well, it's likely this, but it might also be this, or it might be this. And so they were quite effective there. But they have their limitations, these rule-based systems. So if we look at this first wave of AI, it turned out that they were really pretty good at reasoning. As I say, you get chess computers and things like that that could outperform human beings in terms of their ability to play chess, all through these handcrafted knowledge. They had very limited ability to perceive. You could program how to look at the thing. If we go to the tax example, you might input your W-2 form, and it would know how to get the relevant information out of that. So it would be able to do limited perception there. But you couldn't just wave a receipt at it and say, here, take this into account. Like, it is very limited. Had no ability to learn anything. New piece of tax law comes out, it's not like your TurboTax program reads that and thinks, oh, I get it, I know what to do on this. You have to have a human interpret that, add rules. So the system itself had no ability to learn. And it had no ability to abstract. So you might think, well, this means that first wave stuff is old hat, nobody's very interested in it at all. But that's not true. One of the things that we did while I was at DARPA was ran something called the Cyber Grand Challenge. And this was many years of people building cyber reasoning systems using first wave AI principles in cybersecurity. And then the highlight was a competition that we held in Las Vegas, right between the Black Hat Conference and the DEF CON conference. That weekend, we hosted the Cyber Grand Challenge. And so this is one of the big hotels in Vegas. And we had 7 of the finalist machines, and they were all completely separated from human beings. This was a place you could check that there were no cables, and the radio signals in the area were being scrambled and things like that. So there's no cheating. The teams can't access these things. These things now have to work on their own. They're connected together and go, like learn what's going on in the other machine, see if you can see what attacks they might be doing against you, what can you do to defend it, what attacks could you do against them, and what could you do in order to steal information out of these other machines. So you've got these 7 machines all networked together, and they're all now just completely autonomous, trying to figure out how to break into each other and how to defend themselves. And it was quite astonishing. I mean, this whole thing ran, I forget, maybe 12 hours, something like that. And yeah.
So regarding the encryption, since the classical machinery is using PGP keys, correct? So
Well, these were.
yeah. So when we go to quantum computing, how would you think encryption would work in quantum computing?
So I'll happily talk about encryption afterwards,
Yeah.
but encryption isn't part of this story.
Okay.
And trust me, I mean, encryption isn't part of this story, but I'll happily have that conversation with you afterwards. So if you now get these machines attacking one another, let me give you a story that took place here. So one of these machines had got hold, were given the source code of everybody else. In fact, they all started out the same. It studied the source code of another machine. It sort of figured out that there was a particular vulnerability in that source code,